In this video, we look at molecular orbital theory, which is an approximate way of calculating molecular electronic wave functions and energies. To obtain the electronic wave function and energy of a molecule, we need to solve the electronic Schrodinger equation. Doing this exactly is in general not possible, but we can obtain excellent approximations. Here is an example. Take the molecule H2+. It consists of 2 nuclei and 1 electron. The electron is attracted by both nuclei. Therefore, its molecular wave function will spread over the space surrounding both nuclei. However, near nucleus 1, the wave function will approximately look like a hydrogen atom wave function. Near nucleus 2, it will also resemble a hydrogen atom wave function. Therefore, it seems reasonable to approximate the molecular wave function as a linear combination of 2 atomic wave functions. Psi, the molecular wave function, equals C1 times phi1 plus C2 times phi2. Phi1 and phi2 are functions centered on nucleus 1 and nucleus 2. These functions are called atomic orbitals. Or simply AOs. We could use the solutions for the hydrogen atoms as a start. However, we could use other basis functions as well. C1 and C2 are called the linear combination coefficients. Or LC coefficients. Psi is the overall molecular 1-electron wave function. It is called a molecular orbital. Or MO for short. So, the molecular orbital is represented as a linear combination of atomic orbitals, or basis functions. This is the basis of molecular orbital theory. Of course, using only 2 basis functions is only a minimal description, and so we can expect only approximate results. Next, the energy. For the approximate molecular orbital, it is written as E of C1 and C2 equals the integral of psi star h hat psi d tau divided by the integral of psi star psi d tau. Inserting the expression for the wave function, we get C1 squared h11 plus 2 C1 C2 h12 plus C2 squared h22 all divided by C1 squared S11 plus 2 C1 C2 S12 plus C2 squared CS22. Here we have assumed that the coefficients are real. Also, we have introduced abbreviations for the integrals. Hij equals to the integral of phi1 star h hat phi2 d tau. These integrals are called matrix elements of the Hamiltonian. In general, Hij equals to Hji. If the 2 functions are identical, then I equals J, and the integral is called a Coulomb integral. If the 2 functions are different, so I is not equal J, then these are called resonance integrals. The second abbreviation is S of Ij equals the integral over phi I star phi j d tau. This integral is called an overlap integral. It describes the spatial overlap between the two functions phi I and phi j. In general, it is a non-negative number, so Sij larger equal to 0. Also, Sij equals to Sji. If S is 0, it means that there is no overlap at all between the two functions, and a positive value means the two functions overlap in space. If I equals j, then this is the normalization integral. If the basis functions phi I and phi j are normalized, then the integral can be maximally 1. Next, we apply the variational method. Based on the energy expression, we determine the coefficient values that give the minimal energy. For this, the derivatives of the energy with respect to each coefficient are set to 0. The resulting linear system of equations is solved, and solutions for the coefficients are obtained. From these coefficient values, the wave function and the energy can be calculated. With only two functions as a minimal basis, we can't expect a high precision result. However, we can improve this by including more than two basis functions. In general, we expand a molecular orbital, psi, as a linear combination of a number of basis functions, sum over k equals 1 to m of ck times phi k. The more basis functions, or the larger the basis, the better we can model the exact molecular orbital. As basis functions, it is best to choose functions that model the electron probability amplitude well, and that are mathematically simple. Most commonly, Gaussian functions centered on the atoms are used. In summary, we have outlined the basics of molecular orbital theory. The molecular wave function of an electron is approximated as a linear combination of basis functions. These basis functions are often called atomic orbitals, although they are generally not solutions of the atomic Hamiltonian. The energy of the molecular orbital is expressed in terms of Hamiltonian matrix elements and overlap integrals. By applying the variational method to the energy expression, the linear combination coefficients can be determined. With these in hand, the wave function and energy can be obtained.